5.4, conditional probability and independence. A conditional probability is a probability that changes based on the occurrence of some past event. Let's say we flip 2 coins. We can get any of the 4 outcomes in the sample space from both heads to both tails to one of each. What's the probability of getting 2 heads? Well, it'll be 1/4 because all 4 of these outcomes are equally likely. Now let's say we give it a condition, and let's say the first coin flip was a tails. What's the probability of getting 2 heads at this point? Now it's 0% because we know that the first coin was a tails. This is no longer possible. All right, the probability changed based on the condition that the first coin was a tails. Now the conditions for conditional probability problems are often built right into the wording of the problem. So for example, if we know that a randomly selected student can evil eyebrow, what's the probability that the student can talk with tongue? So that red underlined portion is the condition. So that's telling us we're no longer looking at all 200 people in our sample. Okay, we only care about the people who can evil eyebrow. All right, so we're looking at that line right there and only that line. We don't care about this no line here because we know the student can evil eyebrow. They're not one of these people. So to find the probability that yes, they can talk with tongue, now we're just going to take that 42 and put it over the 62. So 67.7% can talk with tongue, given that we know they can evil eyebrow. If we know that a student can talk with tongue, that's this column right there. What's the probability that they can evil eyebrow? So we're only looking at that 149. We don't care about all these no's. 42 out of the 149 can evil eyebrow. Here we have some data on a random sample of 1,526 winter visitors to Yellowstone National Park. They were asked, have they ever owned, rented, or never used a snowmobile? And they were also asked, do they belong to an environmental organization like the Sierra Club? It's arranged in our table here, and we're defining our events as E, they're an environmental club member, yes or no. And then we have our options for snowmobile use, never snowmobile use, etc. So let's find this probability here, but first let's talk about what is this even asking for. So we're being asked to find the probability that someone has never owned a snowmobile, given, that's that line right there, that someone is, yes, an environmental club member. So that's telling us a condition. The condition always comes after that line there, and that's telling us that we're not looking at all 1,526 people in the sample here. We're only looking at the people that were, yes, an environmental club member. These people don't matter. The totals don't matter. Only the people in that middle yes column matter. This is also telling us the denominator of our fraction. There's 305 people that, yes, are an environmental club member. So the denominator of the fraction is going to be 305. Then we can set up our fraction. The 212 is going to go on the top, and that gives us our answer. This one's a little more complicated because it includes 2 events. Given that the chosen person is not a snowmobile owner, what's the probability that he or she is an environmental club member? So the given is that they're not a snowmobile owner. Okay, so they are not one of these groups. Okay, and they could be any of these next ones. Right, what's the probability that they are, yes, an environmental club member? Right, we're talking about these yeses here. And now it's just about setting up the fraction. On the bottom, we're going to have our totals, and they're going to be combined in this case. And on the top, we're going to have the total of our yeses. Now let's do one with a Venn diagram, which can be a bit trickier. What's the probability that a randomly selected resident who reads USA Today also reads the New York Times? So to start, just to figure out what's the given, what's the thing that we know about this resident? We know that they read USA Today because it's telling us that as the condition. And we want to find the probability that they also read the New York Times. If we wrote it out with the standard notation, find the probability that they read New York Times given that they read USA Today. Now, here's the actual fraction for it, and here's how we get that. So the top of the fraction is the intersection, the overlap of the two. All right, and the overlap of the two is that 0.05. The bottom of the fraction is the probability of the given, of the condition. So in this case, the condition is that they read USA Today. That's this circle right here, and that circle totals 40%. So if we think about it another way, of the 40% of people in that orange circle there, 5% read the New York Times. Okay, that will give us that same answer. Next up is the concept of independence. Independent events don't affect the probabilities of one another. Let's say we're flipping a coin. If we flip a coin and we get heads 10 times in a row, it doesn't affect the probability that the next coin flip will be heads or tails. There's still a 50% chance of each occurring. Compare that to drawing a card from a deck. We start off with a chance of 4 out of 52 of drawing an ace. If we pick an ace and we draw another one, now we're less likely to get an ace because there's only 3 out of 51 left. The probabilities have changed. All right, so independent events, the probabilities don't change. Knowing one event occurred doesn't change the probability that the other one will occur. So in other words, if we're given a condition, right, find the probability of A given B, this given doesn't affect the probability of A occurring. It's still going to be the same thing as it was without that condition. This is just that same thing. We're just flipping the B and the A. So let's use that idea to determine whether the events of taco tonguing and evil eyebrowing are independent. So let's say we know a student can taco tongue. That's our given. We want to find out the probability that they can evil eyebrow given that they can taco tongue. So we're going to look at all the people who can taco tongue, the 149. Of those 149, 42 can evil eyebrow. 28.2% can evil eyebrow given that they can taco tongue. All right, does that change based on the condition? So let's say we reversed it. Let's say in this one, we know that they can't taco tongue. Instead of being that first column, they're going to be in that one. All right, in that case, 20 out of the 51 can evil eyebrow. This percentage is different depending on the condition. This is telling us that these are not independent events. Whether someone can evil eyebrow is affecting the probability that they can taco tongue and vice versa. Is there an association between what subject the teacher teaches and which hand they're dominant with? So in our two-way table here, we have dominant hand, right and left. And then we have the subject taught, whether it's math or not math. Are the events teaches math and left-handed independent? So in other words, if we know a teacher teaches math, does that change the probability that they're left-handed? So let's calculate some of these probabilities. We'll start with a given that we know that they're a math teacher. What's the probability that they're left-handed? 7 out of 46, or 15.2%. Now let's change that condition, and let's say we know that they're not a math teacher. They teach English or history or science. In that case, there's 54 teachers, 3 of which are left-handed, or just about 5.5%. These percentages are different. In fact, the math teachers are almost 3 times as likely to be left-handed. So these are not independent events. If we know a teacher teaches math, we know that they're more likely to be left-handed. When we talk about independence, we're really talking just about an association. There's an association between your handedness and what subject you teach, right? And we can see that if we just made segmented bar charts like this. We have our math teachers here on the left. We have our non-math teachers on the right there, and the proportion that are left-handed is much bigger in the math teacher section.